Hello, I'm Zachary Mikas, and I'm going to be talking about supersonic airplanes, and more specifically, the inlet design in the Blackhawk SR-71. I chose this project because I was interested in how you get something to go this fast and what the implications of that are. So when you're traveling that fast, shock waves are created from breaking the sound barrier, which is about 735 miles per hour at the altitude of 10,000 feet. Imagine the wake of a boat. When it's going slowly, circles of rippled water appear around it, and when it's going faster, it creates a wake behind it. This is when the disturbances can no longer keep up with the boat. So what happens is they all form around the boat and come as a wave to the shore instead of smaller ripples. A similar thing happens to airplanes when they're going the speed of sound or higher, because now the sound waves are being outpaced by the airplane, so they can't propagate like normal, so they create a sonic boom. The first supersonic aircraft, which is the first airplane that traveled at Mach 1 or 1 times the speed of sound, was called the Bell X-1. It was created in 1947 by the US military. Now the technology is commonly used in fighter jets by militaries across the world. First flown in 1976, the Concorde became the first civilian passenger aircraft to break the speed of sound. It was built in the UK and France in a joint effort, and 7 Concorde airliners went to British Airways and 7 to Air France. The maximum speed of the Concorde was Mach 2, twice the speed of sound, and it could travel from New York to Paris in only 3.5 hours, less than the normal commercial airline time of 8 hours. It retired in 2003. You may be asking why we don't have supersonic commercial airliners anymore, since they're so much faster than the normal ones. And the main reason for that is, even though we have the technology, it's too inefficient to do that. In this graph, the induced drag is a drag caused by the tilting of the wings that's necessary to give the plane lift. And the form drag is the drag just from going at high speeds through the air. There is the minimum drag that most commercial airliners are close to, because once you start going much faster, the total drag increases exponentially with the velocity. When the drag goes up, the fuel needed also goes up to keep the speed at supersonic levels, and people weren't willing to pay for it. Now I'm going to talk about the Lockheed SR-71 Blackbird. It was a US military plane that was created in 1964 and served with the US Air Force until 1998. Its top speed was 2,200 miles per hour, or Mach 3.2. But first I'll talk about how an airplane engine works in general. So air is taken from the outside through the part called the inlet, which is the opening you see there, and it's put into a high pressure zone and heated up by burning fuel, and then is accelerated out the end, causing a force forward on the plane called the thrust. The SR-71 has to make some adjustments to this design because it's traveling at supersonic speeds. So what you see there is the inlet to the engine of the SR-71. An inlet on supersonic airplanes like the SR-71 has multiple jobs. For one, it needs to decelerate the air from supersonic speeds to subsonic speeds so that engines can handle it. It also needs to divert the shock waves in a way that they're not harmful to the engine. Through the system you see here, the inlet automatically adjusts itself depending on speed and pressure to create the right conditions. The main question I had that I didn't get to look into was what other designs were needed, like the inlet, to make supersonic travel work. A resource I would recommend is the one I highlighted there because it gives a lot of detailed information about the inlet design that I didn't talk about in this video. So yeah, thanks for watching.